All right. Good afternoon, everyone, or good morning, whenever you're seeing this. It's morning here. Been homesick for the last 2 days. I'm still feeling a little tired, but here we go. Okay. So the last couple of days, you've been reading about Kepler's laws of planetary motion. There is a lot of simple mathematical problems you can do that apply to Kepler's laws. Um, we're just going to keep it pretty simple. In the slideshow I gave you yesterday, there's examples, and you can try them if you wish. I am not expecting you to do these calculations. Okay, so don't worry about them. If you're mathematically inclined, you can tinker with them. There's a question and there's a solution, and there's another question you can tinker with if you wish. If this is something that you know that truly interests you. Okay, the first thing when we deal with Kepler's law of planetary motion is the idea that the planets orbit, and we already described it as a circular orbit, right? More precisely, that orbit is an ellipse, right? Instead of a perfect circle, it's a squashed oval. Right? But the eccentricity, how squashed that oval is, right, or that circle is, can vary. Right? So some of the planets there, or most of the orbits, their planets are pretty close to circular, but they're not a perfect circle, so they're somewhat of an ellipse. So when we talk about an ellipse, here is the overall shape. Again, we have to keep in mind that ellipses, they can vary in how squashed they are. If they're a perfect circle, right? Well, you know what a perfect circle is, right? But if they're an ellipse, right, they've got what we call a major axis, right? That is the long axis here. And they've got a minor axis, that's the short axis, right? And then they have two focal points. Okay, the focal points are these specific points found at the middle at the middle of each half of the major axis. And planets in orbit around our sun, their orbits aren't perfect circles, they tend to be elliptical, right? With the sun at one of the focus points. The other focus point, there's nothing there. Right? And planets are orbiting our sun in an elliptical path, but these ellipses are almost circular. They're not perfect circles, though. If they were perfect circles, the sun wouldn't be at a focal point, it would be right at the center. In a planet's orbit, aphelion is the point furthest away from the sun, right? Helion refers to Helios, the Greek god of the sun. Perihelion refers to the point closest to the sun. Okay? So an ellipse has two focus points on the major axis, which is the longest radii, right? And then we have the minor axis, which is the shortest radii. So Kepler's first law is very simple. It states that orbits of our planets are elliptical, with the sun at one focus of the ellipse. So they're not perfect circles. Okay? So in this diagram here, you can see the sun at one focus. The major axis would be here. The minor axis would be here. And the planet is spinning or orbiting around. And there's an empty focal point. And just got to hit pause here for a moment. All right, sorry about that. I'm back now. Okay. The second law, right? Kepler's second law. Right? So in Kepler's second law, what they're referring to is the areas of these sweeps. Okay? So here, closer to the sun, the planet moves faster and it sweeps out a larger distance. But the area of this triangle is going to be the same of this triangle and the same of this triangle, right? the amount of time is the same, right? But the area that is covered from time 0 to time 1, the area of this triangle is the same as the area of this triangle and this triangle. So the radial arm, the line connecting the sun to the planet of a planet, right? Sorry. The radial arm of a planet sweeps out equal areas in equal periods of time, right? And what this shows us is that the velocity or the speed at which the planet moves is faster the closer it is to the sun. And the further away it gets from the sun, the more it slows down. So the planet's moving quickly close to the sun, slowing down as it moves away, moving the slowest here, and then as it gets closer to the sun, its speed increases. So the radial arm of a planet sweeps out equal areas in equal periods of time. So A1 is equal to A2 is equal to A3. This happens because the velocity increases as it gets closer to the sun and decreases as it moves away. So, when a planet is at its perihelion, it is moving at its fastest, while when it is at its aphelion, it is moving the slowest. Kepler's third law. The farther from the sun a planet's orbit is, so let's say we're talking about Mercury really close to the sun and Jupiter a lot further out. Okay? The planets that are furthest away from the sun, they will have the slowest orbits. Okay? They will be moving the slowest. This is a result of not only a greater distance to travel, but a weaker gravitational pull from the sun. So the further away you are from the sun, the slower the planet orbits. Not only does it have a larger distance to cover, but there's less gravity acting upon it because it's further away from the sun, so it's moving more slowly. Mathematically stated, the period or the length of time to complete an orbit squared is proportional to the length of the semi-major axis, right, cubed, okay, or the radius of the orbit. Okay, and with this math, you can do, or with this equation, you can do a number of calculations. Okay. For example, right, if we know how long it takes Jupiter to orbit the sun, we can calculate how far away from the sun it is. Right? And you can work through these calculations. You don't need to. Okay. Here, if you want to try, calculate the semi-major axis or the radius, knowing its orbit, right? And again, you can just use this formula here, which is modified here as a comparison to Earth, but again, don't stress it. Right? The calculation using Kepler's third law can also be used to determine the period or radius of moons orbiting the same planet. So we can use Kepler's laws to calculate and define the orbits of moons around planets. So our moon orbits around the Earth in an elliptical orbit, okay, with the Earth being at one of the focus points. The motions of moons around a planet are the same as the motions of planets around the sun. The moon's closest approach is called perigee. Instead of perihelion, for a moon it's perigee. And the moon's greatest distance from the planet, instead of aphelion, is apogee. Here's a calculation. If you wish to try, go ahead, right, using this formula. You don't need to, though. Okay, eccentricity. I mentioned this term, I think I did, at the beginning of our talk here. Eccentricity represents the how circular an ellipse is. Right? If an ellipse has an eccentricity of 0, it's a perfect circle. If it has an eccentricity of 1, that circle has been squished completely flat. Okay? And the calculation or the equation for eccentricity is shown here. The distance from the center of an ellipse to a focus divided by the length of the semi-major axis. and you can calculate eccentricity. But again, when I taught this class in person, we would do some of these calculations here. I'm not worried about it. Okay,